Okay, graphing polynomials. This is going to be a fun section because we're going to combine everything we've been talking about in the entire unit. It's going to be exciting, you guys. But we're also going to learn about some new features of the graph of a polynomial. So, brace yourself. Okay, so before we talk about some new features about our polynomial functions, we need to kind of freshen up on what even degree functions and odd degree functions look like. So let's take a look at some of these. Okay, these are even degree functions. Okay, we have a degree 2 graph, which is a parabola, a degree 4 graph, so we got a quartic function, and a degree 6 graph. So let's think about some things that are in common between all the graphs. So take a second, think about what is in common between all three of these graphs. You guys are so smart. Even degree functions, if you guys look at the arrows, let's zoom in on the arrows over here. So our arrows, if you see, on this one they both point up, this one they both point down, and this one they both point up. So even degree functions, you guys, always the arrows will point in the same direction, either both pointing up or both pointing down. Okay, another thing you might notice, if you look at the turning points, let's see how many turning points each of these graphs have. So this one has 1, this one has 1, 2, 3, this one has 1, 2, 3. Okay, this isn't a turning point because it's still increasing to increasing. Turning points occur when the graph changes direction. So it goes from positive to negative, or increases to decreases. Okay, or decreases to increases, which this is increasing and then increasing. So that's not a turning point. But anyways, this had 1, 3, and 3. So if you notice, even degree functions have an odd amount of turning points. Holy hot dog, right? Wasn't that cool? Okay, now let's take a look at some odd degree functions. So we got some nice graphs over here. We have a degree 1, a linear function, a degree 3, a cubic function, and a degree 5, which is my favorite, a quintic function. Okay, so let's see what is in common between our odd degree functions. I don't know why I asked you guys these questions. You're so smart. Odd degree polynomials, the arrows point in opposite directions. See, this one points up, then down, then down, then up, then up, then down. Okay, so the arrows point opposite directions for odd, and for even, they point the same way. So we can just look at a graph and automatically know if it's an even degree or odd, which is pretty cool. And kind of like what we're talking about turning points, let's count the turning points on these. This one doesn't have any, it has 0. Okay, because it steadily decreases, never changes directions. This one has 1, 2. This one has 1, 2, 3, 4. So if you guys notice, odd degree functions have an even amount of turning points. Pretty cool, right? Okay, so let's take a look at both. Look at those lovely graphs. Okay, so again, just by looking at the graph, we can automatically know if it's an even or an odd degree function. Now, we might not know what the exact degree is, but we can already predict some nifty things about the graph. Okay, now in class, we either did or are going to do this nifty activity to explore something called end behavior of graphs. So let's talk about what end behavior is. All right, so let's talk about even degree end behavior. So end behavior. What this means, you guys, end behavior, we want to know what happens at the ends of the graph, or where the arrows are pointing. That's at the end of the graph. Okay, if we look back at these graphs over here, the ends of the graphs are where the arrows are pointing. So the end behavior, all we care about is where the arrows are pointing. So remember, with even degree, the arrows are pointing the same way. So they're either pointing up or they're both pointing down. Now, the way that you know if the arrows are pointing both up or both down is by your leading coefficients. So remember, leading coefficients, those are the number, if you write it in standard form, that is the very first number you see. Okay, or if it's not in standard form, the leading coefficient, you find the term with the highest exponent, and whatever the coefficient is of that term is your leading coefficient. So if you have a positive leading coefficient, so if that first number in standard form is a positive number, okay, that tells you where the final arrow points, or the arrow on the right-hand side. So your final arrow is going to point up. Okay, so that will always happen. Even if it's an odd degree function, a positive leading coefficient will make the last arrow point up. Okay, which even degree, since we know both point the same direction, if one points up, the other must point up. Okay, also if you have a negative leading coefficient, that means your final arrow, or the arrow on the right-hand side, will point down, always, no matter if it's even or odd. Okay, and since even degree points the same way, if one points down, the other must point down. Cool, right? All right, now down here, all this funky notation that you guys see, this is called the end behavior notation, and we'll be writing this for our graph. So let's talk about what this notation looks like, which when we read this, you guys, we read down the columns. Okay, these two go together, these two go together, these two go together, and these two go together. So let's talk about what this funky notation means. So this arrow thing, this right here says, as x approaches infinity, the little arrow means approaches. So as x approaches negative infinity. Now what do I mean by that? Okay, if we look at the x-axis, which side is the negative side of the x-axis? Holy hot dog, you guys are so smart. It's the left side. So as x approaches negative infinity, we are looking on the left-hand side of the graph. Okay, so basically when you see this notation, as x approaches negative infinity, all you have to ask yourself is, when I'm on the left-hand side of the graph, what is f of x doing? So this says, as f of x approaches positive infinity. So what you're asking yourself, you guys, on the left-hand side of the graph, where is my arrow pointing? The y value is where the arrow is pointing. Well, since this arrow is pointing upward, it is headed to positive infinity. That's why it says positive infinity. So when you're headed negative on the x, the y is going up. Okay, or on the left-hand side, the arrow is pointing up. So as x approaches negative infinity, the y is going to positive infinity. Okay, as x approaches positive infinity, so which side of the graph has the positive x values? You guys are too cool for school. It is the right-hand side of the graph. Okay, so on this side, we're saying as x approaches positive infinity, or when it's on the right-hand side, where is the graph pointing? Okay, well the graph's pointing upward, so that means the function is headed toward positive infinity because it's pointing up. So if your arrow is pointing up, you guys, it's approaching positive infinity. It's headed in a positive y direction. Let's look over here. So as x approaches negative infinity, so we're still on the left-hand side, where is the arrow pointing? Well, it's pointing down. Down where the demon cats lurk, so watch yourself. And downward on the y-axis is at negative infinity. Okay, so as x approaches negative infinity, f of x approaches negative infinity. Or on the left-hand side of the graph, the arrow points down. That's kind of the lame terms for that. All right, and then as x approaches positive infinity, so on the right-hand side of the graph, where does the arrow point? Well, guess what, you guys? The arrow is still pointing down, so it's approaching negative infinity. So that is what end behavior is, you guys. Okay, so that's what it looks like for even degree. Okay, odd degree function, same idea, except with odd degree, our arrows point opposite ways. Guys, so no matter what, if you have an odd degree function, the arrows must point in opposite directions. And again, the way that you know which way the arrow points is all based on your leading coefficient. So like before, if you have a positive leading coefficient, that final arrow on the right-hand side will be pointing up, which means the first arrow must point down since odd degrees go opposite ways. Okay, and if you have a negative leading coefficient, your final arrow on the right-hand side will point down. Bam. Okay, so which means the first arrow has to point up since odd degree, the arrows point opposite ways. Okay, and then down here, remember, this is our end behavior notation. So as x approaches negative infinity, or on the left-hand side of my graph, the arrow is pointing downward, which means it's headed toward negative infinity. Okay, and as x goes to positive infinity, or on the right-hand side of the graph, where is the arrow pointing? It's pointing upward, which means f of x is approaching positive infinity. Okay, so basically with end behavior, you guys, you say, what happens on the left-hand side of the graph? What happens on the right-hand side of the graph? You always have these x's right here. You always have one x headed to negative and one x headed to positive, always. The thing that's going to change is your f of x. You tell me where the arrow is pointing, and that would be your answer for the end behavior. Okay? So, on the other one, as x approaches negative infinity, the graph is headed to positive infinity. So on the left-hand side of the graph, the arrow points upward. Okay, and as x goes to positive infinity, or is on the right-hand side of the graph, the arrow is pointing downward, which means f of x is headed to negative infinity. Okay, so again, the x part always stays the same, you guys. Do not change these x's. The y's, or the f of x, is the part that will change. Okay, so even if you look back here, if we go all the way back to this slide, do you guys see that the x's are the same? Negative, positive, negative, positive. The y values, or the f of x values, are the parts that change. So just keep that in mind. Again, over here, same idea. Okay, if I get these back up, negative, positive, negative, positive. The x, we always want to know what happens on the left, what happens on the right. Again, the y's are what change. So let's keep going, because I know you're tired of me saying that over and over. Okay, guys, we have gotten to our first in-class example. Example 1 and example 2. So you will be drawing these graphs in your handy-dandy notebook. Okay, and what we're going to do is discuss the end behavior of the graphs by looking at the graph. So on the first one, I want to know, is this an even or odd degree? Which, we need to look at the arrows to determine that. So one arrow is pointing down, and one arrow is pointing up, which if we think back to here, odd degree functions have one arrow pointing down and one pointing up. So this is an odd degree function, you guys, because we have arrows going in opposite directions. Okay, now I want to know if the leading coefficient is positive and negative. Now to determine that, you always look at your final arrows, the arrow on the right-hand side. Since this is headed upward, it's headed in a positive direction. So your leading coefficient will be positive because the last arrow points up. Now the end behavior. We say when x is on the left-hand side of the graph, what is it doing? Well, it's pointing down. And on the right-hand side of the graph is heading upwards. Okay, so our end behavior, you guys, when x is headed to negative infinity, or on the left-hand side, f of x is headed downward to negative infinity. Remember, read this vertically. And as x is on the positive side, as x has the positive infinity, the graph is pointing upwards, which means f of x is headed in a positive direction, so positive infinity. And that's it on that one. Fun times, right? Okay, so if you want to try example 2 on your own, go ahead, pause the video, and see if you get it right. All right, so example 2, even or odd degree. Well, I must look at the arrows to determine this. So since my arrows are both pointing downward, they're both pointing in the same direction, which makes it an even degree. Even degree always points in the same direction. Odd degree points in opposite directions. Okay, the leading coefficient, is it positive or negative? Okay, and LC, that's my abbreviation for lead coefficients, if you didn't figure it out. We always look at our final arrow on the right-hand side to determine if our leading coefficient is positive or negative. Since my last arrow is pointing downward, if you see here, that means the leading coefficient is negative because that last arrow points down. All right, guys, end behavior. On the left-hand side of the graph, what's the graph doing? It's pointing down, so it's headed to negative infinity. And as x approaches positive infinity, or on the right-hand side of the graph is also headed downward, so f of x is headed to negative infinity. Okay, so again, as x goes to negative infinity on the left-hand side, y goes to negative infinity. As x is going to positive infinity, f of x goes to negative infinity because it's pointing down. So again, the x part always stays the same. It's the y that could change. Awesome job on that example, you guys. Let's keep going. So now, this is a funsy. You'll have to wait to do that one. Now we're going to do the same thing, but without a graph this time. This time, we're solely going to look at the equation. So let's see what happens. So first of all, I want to know if this is an even or odd degree, which, to determine the degree of the polynomial, I must find my highest exponent, which I spotted right here. It is not in standard form, you guys, so be careful. Sometimes I'm sneaky and I don't put things in standard form. Okay, so my degree is 4. Okay, that's my highest exponent, which is an even degree. So this is an even degree. It's degree 4. Okay, I want to know what the leading coefficient is. Well, the leading coefficient is with my term that has the degree. So my degree was x to the 4th. So the leading coefficient of that is negative 4, which makes it a negative leading coefficient. So my end behavior, let's think about it. Okay, we have to combine these two pieces to know the end behavior. So if it's even degree, my arrows, where do they point? Same way or opposite way? Holy hot dogs, you guys are so smart. Even degree means the arrows point the same way. So they're either both pointing up or both pointing down. Now it's this leading coefficient that tells me which way they point. So since it's a negative leading coefficient, that tells me that my final arrow on the right points down, which since it's even degree, both have to point the same way. So both point down. Since the one on the right points down, the one on the left points down. So this will kind of help you with your end behavior, you guys. This arrow talks about what happens on the left. This arrow talks about what happens on the right. So as x heads to negative infinity, the graph heads down to negative infinity. And as x heads to positive infinity, the graph heads down to negative infinity. So that would be my end behavior. On the left-hand side, it heads down, and on the right-hand side, it heads down. Holy hot dog, you guys. All right, if you want to try example 4 on your own, go ahead and pause the video and try it out. See what magical things happen. Okay, so even or odd degree. Again, I need to know the degree first to know if it's an even or an odd degree. So my degree is the highest exponent, which the highest exponent I see is this right here. So guess what, you guys? This one's already in standard form. So my highest exponent is x to the third, which 3 is an odd number, so it's an odd degree. My leading coefficient, well, I don't see anything in front of my x to the third. So secretly, there's a 1 hiding out there. And 1 is a positive number. Okay, so my leading coefficient is a positive number, and it's an odd degree. So my end behavior, it helps if you guys kind of know the arrows and where they're pointing. So, since it's a positive leading coefficient, that tells me my final arrow is going to be pointing up. And since it's an odd degree function, the arrows point opposite ways, which means my first arrow points down. So this tells me what happens on the left-hand side. This one tells me what happens on the right-hand side. So as x heads to negative infinity, or when you're on the left-hand side, f of x is heading to negative infinity because it points down. And on the right-hand side of the graph, so as x goes to positive infinity, the graph points up, which means f of x heads to positive infinity. So on the negative side of the x, y is headed down. On the positive side of the x, y is headed up. Pretty cool, you guys, right? Awesome. Here's a funsy, so wait on it. Okay, now, example 5 and 6. These are doozies, you guys. Okay, we're combining everything we have talked about in this entire unit into these two problems. It's going to be thrilling. Okay, but I'm not going to give anything away right now. You're going to have to pause the video and learn how to graph polynomials using all this nifty stuff that we talked about. So you'll be answering parts 1 through 10, which it looks more intimidating than it is. I promise you guys. All right, and example 6, again, same thing as example 5. So if you guys think you understood example 5, go ahead and try example 6 on your own and see if you get the right answer. Okay, otherwise follow along on example 6. Okay, so example 6, we're doing the same thing. Eventually, we're going to be graphing this lovely polynomial, going through all this nifty stuff. So go ahead and pause the Prezi video and watch example 6. Holy hot dog, you guys. Alright, now I know you guys had a blast on example 5 and 6. So in class, I know you'll have a stellar time on this funsy, but you'll have to wait on it. Okay, the next phase, we're going to talk about some other key features of the graph. Okay, so we're going to talk about turning points, which we've talked about turning points already. Turning points are where the graph changes direction. So it goes from increase to decrease or decrease to increase. Okay, so basically, guys, turning points are kind of the little humps on the graph, kind of at the top of the mountains or in the valleys, kind of how I look at it, or you can visualize it. You're either on the top of the roller coaster about to scream down to your death, or you're at the bottom of the roller coaster where you can breathe for a second. So this graph, the turning points are at these points right here. Okay, and you guys, be careful. Turning points are points. So if I ask you, what are the turning points? I need to see points actually listed. So the points would be -3, 2. This is -1, -3, 2, 1, and 4, -1. Those are the turning points on the graph, or where the graph changes directions. Okay, So turning points. Okay, we did a nifty activity in class where you found out the most or the largest amount of turning points that a graph can have in relation to its degree. So again, turning points where the graph changes direction. So it goes from increase to decrease or decrease to increase. Okay, so these are our turning points right here. We got one there, and one there. Pretty nifty, right? I think so too. Okay, now, the largest amount of turning points is 1 less than the degree. Okay, so the most turning points that a graph can have goes up to 1 less than whatever the degree is. So if you have the degree, basically to find the amount of turning points or the largest amount of turning points, you just subtract 1 from the degree to get your turning points. So like if you have a degree 4 graph, like this is kind of what a degree 4 looks like. It's not necessarily degree 4, but it's what it looks like. Okay, the most it can have is 4 minus 1, which is 3, which if you look here, it has 3 turning points. 1, 2, 3. So if you know the degree, to get to the amount of turning points, you subtract 1. Now here's another statement, kind of the reverse of the first one, you guys. Okay, from a graph, the smallest degree a polynomial can be is 1 more than the number of turning points. Okay, so we'll talk about why I'm calling this the smallest degree in a moment, but if you want to know the smallest degree, if you know the number of turning points, what you have to do is basically just add 1 and you'll get the smallest degree that it could be. Now the reason why I call it smallest degree, you guys, let's think about it. Okay, technically, we know that this graph right here is an even degree because they're both pointing upward, the arrows. Okay, and let's look at this statement right here. It says the largest amount of turning points, the largest amount of turning points is 1 less than the degree. So that means it could have less than 1 less than the degree. So technically, you guys, this could be like a degree 10 graph because 3 is definitely less than 10, and the most that a degree 10 graph could have is 1 less than it, which is 9. Okay, that's the largest amount of turning points though. Okay, so that's why we say the smallest degree that it could be is 1 more than the turning points. Okay, so again, if I give you the degree, sorry guys, if I give you the degree to find out the largest amount of turning points, subtract 1 from it. If you have the turning points to get the smallest degree, add 1. Just like in this problem, it has 3 turning points in it, so the smallest possible degree could be is 4 because 3 plus 1 is 4. Now, if that didn't make sense, I promise it'll make more sense in the nifty example problem. So let's look here. So I have this chart here to kind of help us out. Okay, so it says, what is the lowest degree of the polynomial? So this is example 7 and 8. Okay, go ahead and sketch the graph. It does not have to be a perfect graph, just do your best shot. Okay, so first, we're going to talk about the number of turning points. So let's count them up. It's where the graph changes directions, which I see 1, 1, up. There are 4 because I see 1, 2, 3, and 4. There are 4 turning points. Okay, is this function even or odd degree? Well, let's look at the arrows. My arrows are pointing in opposite directions, which means it's an odd degree. And finally, the lowest degree, it could be. So I have the number of turning points. If you see, I have the 4. Okay, so to get to the degree, I just add 1. So 4 plus 1 gives me 5. So the smallest degree that this bad boy could be is degree 5. Cool, right? Okay, now, example 8 is very similar to example 7. So if you think you've got example 8, go ahead and pause the video and try example 8 on your own, you guys. All right, number of turning points. There are 2 because I see 1 and 2. Bam, there's 2 turning points. Even or odd degree. Again, we look at the arrows on the ends of the graph to see if it's even or odd. Well, this one's pointing up and this one's pointing down, so since my arrows are pointing in opposite directions, it is an odd degree function. Cool beans, right? All right, and the lowest degree it could be. So since I have 2 turning points, I have my turning points to get to the degree, you add 1. So 2 plus 1 is 3. So the smallest degree of this bad boy right here could be in example 8. It's a degree 3 graph. Pretty nifty, right? Okay, we have one more thing to talk about. This will be the funsy we're going to do, but you got to wait on that. Okay, we have one more thing we're going to talk about in class, and this is called extrema. extrema, which these are the extremes of the graph. Okay, and the extrema we're going to talk about are things called absolute maximums and minimums. So you want to know the absolute maximums and minimums in the problem, and then something called relative or local maximums and minimums. Okay, so these are things, you guys, that could either be the absolute max or min, or relative means they could be playing it off like they're the max or min, but they're actually not. Okay, so in class, you guys went through and you labeled what you thought the maximums and minimums were, and then specifically what the absolute maximums and minimums were. So let's talk about what these things are. All right, so our extrema, the different kinds of extrema we have. Okay, now, extrema, they must occur at the turning points. Okay, all extrema is at turning points. If you think the extremes are at the arrows, these are not extrema, you guys. We cannot have infinity be an absolute or a relative maximum or minimum. Okay, infinity can never be the answer. Our answer must always occur at a turning point. Okay, so first we're going to identify the turning points, and then we'll label them as either absolute or relative maximums or minimums. So, an absolute maximum is the absolute highest point on the graph. Okay, so this means there's no other point on the entire graph that is larger or smaller than this point. An absolute minimum means there's no point on the graph that is lower than this point is, the lowest possible point on the graph. Okay, and remember, infinity cannot be the answer. Okay, so sometimes, you guys, graphs don't have absolute maximums or minimums, and that's okay, because sometimes the absolute highest and lowest points occur at infinity, which means it can't be an extrema because extremas occur at turning points. They're a point. So like if we look over here, you guys, this one has an absolute maximum because if you see here, the blue point right here is the highest point on the entire graph. Okay, now this one doesn't have an absolute minimum because the lowest points are headed toward infinity, and infinity can't be the answer. All right, now let's talk about what a relative or a local max and min are. Okay, so relative or local maxes and minimums. They want to know if you took like a chunk of the graph and you only looked at part of the graph, would that part be the maximum or minimum of just that one part of the graph? Okay, so like if we look over here at this relative maximum, if I kind of ignored the left-hand side of the graph and only looked at this part, you guys, this would be the maximum on this part. So that's why we call it like a relative or a local max. Now basically, you guys, the way I know, or the easy way, you find the turning points. If your turning point is not the absolute highest or lowest point, that means it's either a relative max or min. Okay, so if it's playing it off like it's a maximum, it looks like it's a maximum, but it's not, it's called a relative maximum. If it's playing it off like it's a minimum, but it's not the absolute lowest point, then it's a relative minimum. Okay, so again, relative maximums and minimums are not the highest and lowest points on the graph, but they kind of appear to look like one. Okay, they're sneaky ninjas. They play it off like they are max or min, but they're not. Okay, now, there can be more than one relative max or min. Okay, if there's more than one point, you guys, that occurs at a turning point, and it's not the absolute highest or lowest point, then they're all going to be relative maximums or minimums. So you can have more than one of these. So keep that in mind. And it's also okay, you guys, to not have any absolute maximums and minimums. So absolute maximums and minimums. Sorry, that sounded funny. Okay, let's go on. So, we're going to state all the relative and absolute maximum and minimum points. Okay, so go ahead on example 9. You're going to sketch this graph. It does not have to be a perfect sketch. Well, try to make it as accurate as possible. And we're going to be labeling points at the turning points. So before I can state relative and absolute minimums and maximums, I must know where the turning points are. And when I find that point, I have to determine if that point is the absolute highest or lowest point. If it's not, it's going to be some sort of relative max or min. So I'm going to work my way from left to right and label all the turning points on the graph. So this first one, you guys, I said it's a relative minimum at -3, -4. Now the reason why this one's a relative minimum, you guys, is because if you see, this is not the absolute lowest point on the graph. There's a point that goes lower than it. So it's not the absolute minimum, but it's the relative minimum. It looks like a minimum, but it's not the absolute one. All right, let's work our way over. Now this one, you guys, I called it a relative maximum at, it's about at -1.5 and 1. Again, I'm just approximating. And the reason why it's a relative maximum, there are points that are higher than this point. This is not the absolute highest point on the graph. Okay, so since it's not the highest point on the graph, but it looks like a maximum, it's going to be called a relative maximum. Again, this is a relative minimum because it's not the absolute lowest point on the graph, but it looks like a minimum kind of point. And it's at the point 0, -1. So again, you guys, these are actual points. So if I ask you what the relative and absolute maximum and minimum points are, I better see a point listed. All right, next one. Relative maximum because it's not the absolute highest point, but it's playing it off like it is, and it kind of looks like a maximum. And lastly, this one's a little different, you guys. This is actually the absolute lowest point the graph will ever reach. Isn't that cool? So since it is the absolute lowest point the graph will ever reach, this is the absolute minimum at the point for -8. Okay, our last example problem. Okay, I already had the turning points labeled for you, so all you have to tell me, you guys, are these turning points maximums or minimums, and also are they relative or absolute maximums and minimums? Okay, so if you understood example 9, go ahead and pause the video and watch example 10. So on this one, which I wanted to make one comment actually, you guys, if you see here, it is okay to have more than one relative maximum and more than one relative minimum. Okay, and it is okay to have just one absolute minimum or maximum. You can't have more than just one. The graph is either going to reach a highest point or lowest point, but sometimes it never reaches it. So let's talk about it on this graph. Okay, I'm going to work my way from left to right and let's see what happens. This is a relative maximum at -3.2 because it's not the absolute highest point, but it is kind of on top of the mountain or kind of like a maximum. This one's a relative minimum because it's not the absolute lowest point. The graph's going to keep heading down, okay, and it's kind of at a minimum looking kind of point, so it's a relative minimum. This one's a relative maximum because it's not the absolute highest. The graph's going to keep heading upward, but it is kind of a maximum looking kind of thing. And finally, this point right here is called a relative minimum because it is not the lowest point on the graph. This point goes lower than this one. Okay, and the graph still even heads down further. So it's not the absolute, but still looks like a minimum. So if you see, you guys, on example 10, it didn't have any absolute maximums and minimums. And that's okay, you guys. It's okay not to have any. Holy hot dog, you guys. That was an incredible section. I love graphing polynomials, and I hope you guys do too.